Thank you for Professor Sakajo. So I'm Hironori FUDEYASU from Yokohama National University. So I'm very honored to be here. And so before starting my talk, so I'd like to express my appreciation to all of the PI researchers and the staff involved on this project for the continuous hard work and great effort. Okay, so the title is a Typhoon Control Research, so aiming for the safe and prosperous society. Okay. Okay, so under the Japanese national project, Moonshot, so we are working on the typhoon control research. So I refer it as a typhoon control, but in reality, it means reducing the typhoon intensity through the human intervention. It is not truly controlling typhoon how we want. So our project aims to develop the principal and fundamental techniques to reduce that typhoon intensities through the human intervention using the numerical simulations. So previous typhoon studies have shown increase in the typhoon intensity due to the climate change, including global warming. For example, there were 5 to 10% increase in the maximum wind and 20-30% increase in the precipitation level related to the typhoon intensity. So our goal is to actually reduce the typhoon intensity increased by the climate change to the level that our current infrastructure can mitigate the damage. The level means the 5 to 10% for the maximum wind speed and 20-30% for the precipitation level. So here, okay, I'll skip this. So here is a research organization chart. So we gathered experts, So we bring together members from various fields across Japan at a Moonshot research core team. So here is a categorize our approach into the 5 distinct groups. Sorry, I want to change the point. Okay. So we just categorize our approach into the 5 distinct groups: methodological approach, mathematical approach, engineering approach, impact assessment, and LC. So I'll give you a quickly overview of what each team has achieved so far. The first, methodological approach. So they are investigate a possible control method that could affect the typhoon intensity or typhoon structure using the numerical simulations. So here is an overview of the intervention method for the typhoon proposed by the methodological approach. So, over the past 3 years, so we examined the similar 40 intervention method here. But so based on these previous findings, so this year we have concentrated on the crowd seeding based interventions. So that's one of the results. So this movie is one of the simulation result assuming the crowd seeding. So here, so white color represented the typhoon clouds, and green, you can see the green parcels, crowd seeding particles. Crowd seeding particles are advected by the wind and transport into the inner core structure to enhance the cloud formation. So this simulation result was obtained using the aerosol coupled model, so named scaled sprinters. So this model includes similar aerosol species and sizes, which are explicitly advected by the winds, 3-dimensional wind. And also the aerosol cloud interaction is considered. For the crowd seeding experiment, so we just target region for the crowd seeding was determined by the tracking the TC center here. So and only in the convective region at 5 meters height. And also the similar cloud seeding experiments were conducted by the changing the locations. For example, inner rain band here or outer rain band according to the radial location of the TC center. And also that changes the amount of the seeding material released. So here is the result of the seeding experiment, inner rain band or outer rain band. So this figure shows the time series of the central sea level pressure from various experiments, and also here is the maximum wind speed. And the gray shade show the intervention period. So we just started the intervention as a typhoon started to develop for the 6 hours. And here is the same as that. And also the black curve represents the experiment without seeding. That's a no seeding experiment or control. So comparing the control, black curve, the seeding within the outer rain band here, so enhance the degrees of central pressure with a maximum wind increase. So this response implied that the seeding within the outer rain band induce an intensification of the simulated typhoons. So on the other hand, so that seeding within the inner rain band here, so suppress the degrees in the central pressure with the maximum wind weakening. So this response implied that the seeding within the inner rain band induce the weakening of the simulated typhoons. The amount of the seeding used in this experiment, so similar, 75,000 tons or similar 100,000 tons or a million tons. So that's a which is quite large, but and not feasible for the human intervention. But so we now try to the seeding experiment to find out how change the structure or intensity. So now moving forward, we need to focus on the upline seeding where and when it can be truly effective. So collaboration with other fields such as a mathematical approach. But I'd like to emphasize, so this contrast, so inner rain band or outer rain band is very clear and consistent. So that's a very, very important findings. So here is a study which examined why the cloud seeding, enhanced cloud seeding induce a TC weakening. So previous study, so Rosenfeld, it's a very famous paper, so proposed a cloud seeding within the outer rain band here, induce a TC weakening. That is opposite to our result. So they mainly explain the convection in the outer rain band decrease the inflow toward the eye wall, leading to the weakening of typhoons. But our theoretical study showed a new secondary circulation to maintain the gradient wind balance, which can be captured by the balance dynamics framework. So we find inner rain band so can weaken the maximum wind through the two process. So here, so that's a typical secondary circulation to intensify the typhoon intensity. But so when the inner rain band developed, so diabatic heating in the eye wall decreased, so leading to the weaker secondary circulation, which directly reduce the spin up of the maximum wind. That's the first mechanism. And also the second mechanism, so the inner rain band diabatic heating, so developed the new secondary circulation around the heating to maintain the gradient wind balance. So in the new secondary circulation, so inflow on the outer side of the heating, diabatic heating, or outflow on the inner side of the diabatic heating. So that outflow near the radius maximum wind directly cause a spin down of the maximum wind. That's a second mechanism. So this second mechanism is smaller than the first mechanism, but account for about 5 to 10% negative effect for the total tendency of the spin up. That's a much the weakening target set in the project. So if you are to try to actually weaken the maximum wind through the cloud seeding, the effective strategy would be to enhance the diabatic heating just outside the eye wall. So here's Rosenfeld. So we discussed about this process and his process on this Monday and Wednesday. So he accepted our theory. Okay, so metallurgical study obtained some interesting results, and similar findings also appeared in the mathematical approach. So mathematical approach is investigating the physical locations that have significant impact on the typhoon intensity using the sensitive analysis method. So P.I. Ito developed a new sensitive analysis method named the cycles of the short wind sensitivity analysis coupled with adding the perturbation using a high resolution realistic model. So he said a joint-based sensitive analysis is a very, very powerful tool, but for simulate typhoon intensity, high-resolution model is necessary. And strong non-linearity developed after just a few hours. So to resolve this problem, so we propose a multiple 1-hour sensitivity windows. So each coupled with small perturbation to capture the time evolving sensitive like this. So here is one of the results. So radius height cross section of the water vapor sensitivity related to the typhoon intensity. So you can see here, so positive signal. So positive signal indicate that so signal here that developed in the radius of 30-40 kilometers, which is corresponding to the eye wall. So this means increase the moisture in the eye wall, enhance the typhoon intensity, which makes sense physically. But I want to show that here. So negative signal. So negative signal just outside the eye wall indicate that the decrease in the moisture here enhance the typhoon intensity. But on the other hand, so the increase in the moisture, like convection in a rainbow diabatic heating, contribute the typhoon weakening. That's a very So this result is very consistent with the findings obtained by the methodological approach, as I told you, the last slide. Okay, so if, as suggested by the methodological study or mathematical approach, the release of the diabatic heating through the cloud seeding can lead to the typhoon weakening. So the question is, what method could actually make such cloud seeding possible? That's an engineering approach work. So when considering the possible approach to cloud seeding, the first option is use of the aircraft. So engineering approach is examine what type of the aircraft could carry large quantities of the cloud seeding materials. So for example, the Kawasaki C2 aircraft. So this aircraft can carry up to the 36 tons for materials per aircraft, and with a maximum range 4,005 kilometers. So when fully loaded, and also the cruising speed is over 800 kilometers per hour. So such a large aircraft are very costly. So each unit costs 30 billion Japanese yen, and the signal operation cost a few million Japanese yen. So please remember this number. But so the next option is use for the ships here. So maximum payload over 10,000 tons for each ship, and maximum range about 25,000 kilometers. So ships can carry much larger payload than aircraft, and also ships are far more cost efficient than aircraft, although aircraft can travel much faster than ships. So now we talked about the cost. The question is, can weakening the Typhoon really provide enough benefit to just very high cost? So that's an impact assessment work. So impact assessment team is examining the potential benefit to society if the intervention successfully weaken the typhoons, so in terms of the reducing the typhoon damage. So one of their team, the PI Kato, developed the wind disaster model for typhoons, each typhoon, to estimate the amount of the damage caused by the different wind speed. So this figure shows a change in that economic loss for Typhoon JB case, one case. So the horizontal axis is a percentage change in the wind speed, and the vertical axis is a change in the economic loss. So when the wind, so that's a real world, and when the wind speed changed by plus or minus 10%, the number of the damage incident generally increased by the factor of about 3.5 to the real world, or 1/3 from degrees to 1/3. So this also translated to a reduction in total damage cost of about 870 million for this case due to the 10% degrees of the maximum wind. So that's a 800 million Japanese yen is larger than the cost. That's a good point. So okay. So this is a cases depending on the case. So this is a fact size case. So 680 billion Japanese yen by 10% decrease in the maximum wind. So building the damage is very highly sensitive to the wind speed. So actually weakening a typhoon can be very effective. Okay, so finally LC. So LC team is collecting the outcomes from each group and work to identify the key challenges that must be addressed for the social implementation by 2050. Here. So here is a summarize the main challenges in typhoon control through the cloud seeding. So in our experiment, we assume the use of the seeding material, so dry ice or silver isolate or something like that, and key factors that determine the effectiveness of the cloudness. So there are 3 points. One is the amount of the seeding material released, and also the physical form and stability during the transport, and seeding location and method. So however, there are several practical challenges. One is establish a stable supply chain for the seeding materials. So we assume the use of the, so we need to ensure that these materials can be produced, stored, and transported safely in the large quantities. And another challenge is developing an effective system for the operation. So not only by aircraft, but potentially also using the ships or independent platform in the future. So address these challenges will be the essential to real world applications. Okay. So finally, I'd like to introduce another approach. So other method. So unlike cloud seeding, so another methodological approach team focus on using what already exists inside the tropical cyclones to release heating more efficiently. So this figure shows the numerical simulations for the distribution of the super cooled water droplet in the TC inside the typhoon. So here is the typhoon center, and here is the distribution of the super cooled water droplet. And so in this experiment, we conducted a simulation in which all supercooled water droplet within the 50 kilometers radius of the center were actually frozen for only 1 hour. So that's named the artificially freezing the experiments. So this figure shows one of the artificially freezing experiment results. So time series of central pressure and the maximum wind speed. And comparing to the control arm, black curve, so artificially freezing experiment, blue curve, show a clear difference about 2 days after the intervention, freezing intervention. So the pressure increased by the 40% and the maximum wind decreased by 50 meters per second. So this result suggests that if secondary supercooled water droplets actually exist in the real typhoon, and so supercooled water droplet could be artificially frozen in some way, so there must be a potential for typhoon weakening. So, but so that's an important question remains. So, do these promising the supercooled water droplet actually exist inside the real typhoons? So, to answer this important question, we conducted the aircraft observation for this month's typhoon to evaluate, to find out the supercooled water droplet. So this photo shows the observation aircraft just before the takeoff from the Nagoya airport. So this observation aircraft is particularly, especially modified for the meteorological observation. So it has a shooter system to release the drop zone there. So we have 2 aircraft flights for this typhoon. So the first day, the typhoon was located here, the south of the Japan, and from here we started to go to the typhoon to observe. And the second day, so typhoon has approached the Japan, and we observed here. So this photo shows the nose-mounted radar observing you can see the eyeball and eye. So after this, we penetrated the eyeball. So this. Okay, so this movie was taken from the aircraft wings, and while passing through the eyeball, so aircraft was shaking. So Tsuboki-san said, it's not too bad, but for me, I felt a bit scared. But so once intervened the typhoon, so Typhoon I, so shaking stopped completely. And then, so we, circled inside, so we could see the ocean below us in the eye. So we can see the cyclonic clouds are there, but small, only the lower troposphere. And then, so aircraft leveled again, and also we could see the building eyeball surrounding us like this. And then, so we penetrate eyeball again once more to observe the supercooled droplet. Okay, here is some of the preliminary results from the drop zone observations, and the particle profile on temperature, relative humidity, and wind, and for the inside the typhoon eye and eye wall. And so please focus on the black dots or black wind bulb. They represented our observation result, while the blue line shows the simulation results. So you can see the relative humidity, the mid and upper troposphere is relatively dry in the eye, while the eyeball region is nearly saturated. And also the relative humidity is relative to the water saturation, and you can see the dashed line is ice saturation vapor pressure corresponding to the 100% water saturation. So when the observed humidity value to the right of the dash line at the temperature below the 0.2 degree, so here and here, so it means liquid water exists even below freezing, above the freezing level. So this observation results suggest the possible presence of the supercooled water droplets. So but now the data analysis is still ongoing, and we look forward to the sharing more detailed results soon. Okay, conclusion. So we are investigating whether typhoon intensity or typhoon structure can be reduced or changed through the human intervention, so using the numerical simulations. So numerical experiments suggest several possible methods, but cloud seeding has been found to be the most effective intervention so far. And each team has already produced a meaningful result, which will guide the next phase of our project. There are some remaining challenges. So the required intervention amount for the cloud seeding are still far beyond human ability. So we need to identify more efficient or small-scale intervention method in collaboration with other experts, such as a mathematical approach. So from weakening the typhoon intensity to the reducing typhoon damage is so next stage. So this stage, our main goal was to investigate whether typhoon intensity can be reduced by the human intervention. But based on these achievements in this phase, so next phase will shift its focus toward interventions that can actually reduce typhoon damage, which has been our ultimate goal from the starting point. Okay, thank you so much. That's it.
Thank you very much, Dr. Fudeyasu. So, dear participants, do you have any questions or comments?
Very excellent talk. I have just a comment on mathematical approach, especially on joint sensitivity result. Could you show that graph? You showed the sensitivity with respect to water vapor on typhoon intensity here.
Yes.
And if you compare the magnitude between the positive and negative area, adding more vapor to the blue area means it can reduce down the typhoon intensity, but not many, right? But if you decrease the water vapor in the red area there by the same amount, then the effect of typhoon intensity decrease will be much higher, right? So in that sense, that's a good interpretation in scientific sense, but in practical sense, how can we reduce down or increase the water vapor inside the typhoon? It's very hard to do that. If we do cloud seeding, it means it can increase the mixing ratio of cloud water or ice particles, right?
Yes.
So probably doing the sensitivity or joint the sensitivity with respect to mixing ratio of cloud mixing ratio or ice mixing ratio would be more practical rather than doing water vapor sensitivity.
Yes.
Okay.
Thank you for your efficient comments. So we will do that. So that's why we are working together. So each group, so from the scientific point or from the engineering point or mathematical point like this. So one, yes, thank you so much. So I'll do that.
Thank you for the nice presentation. I had a question on the definition of your typhoon control at the beginning. I was glad to see you define that better. And you're focusing on the intensity, generally with the maximum wind or central pressure. What about, are you considering the effects of rainfall amount and rainfall accumulation from a typhoon? And are these sensitivities that you've been testing to impact the intensity? How is that going to change speed or amount of rainfall that could come out? Because we see in many tropical cyclones, some of the biggest impacts aren't just the wind, but are the actual rain and flooding that it comes along with it.
Yeah, thank you so much. So, yeah, it's hard to correctly answer because we can't do that. So, this rainfall is related to the typhoon or something. So, but our ultimate goal is to reduce the damage related to the typhoon caused by typhoon. So, not so important for the definition of the rainfall. Just we check the damage, how to reduce the damage or something. So it's a so anyway. So my answer is we haven't decided rainfall from the typhoon or other phenomena.
Again, thanks for
Yes.
the excellent talk. So maybe a related question.
Yeah.
So for example, for the typhoon, storm surge is also an important thing that caused the damage. And so in this evaluation for economic loss, you use the TC intensity in terms of the central pressure and also the maximum wind speed. How about the TC size? Because there are also conditions that even with the same intensity, the TC size can be very different, and that can create a large difference in the storm surge event. So is it possible that in your economic laws that the equation or in the future the framework can those parameters be also considered? Thank you.
Thank you so much. So one of our groups investigate how degrees of the storm surge due to the modified typhoon intensity is quite different due to the change of the typhoon intensity, like a wind, maximum wind or speed or something. But the size is very sensitive for that. So it's hard to yeah. But now we are working on that. So thank you so much. Your point. I passed that my colleagues.
So I have a comment about the definition of the term control. You said that changing the intensity is not really controlling, but my understanding is a little bit different. So the control is we take some actions and to reach the goal of the control. So it's not just changing or modifying the phenomena, but we have some target trajectory of some target, and then we take some actions. If you think about driving a vehicle, we make some actions and manipulate a machine or vehicle to control, right? So it's the same to me. If you target, let's say, weaker typhoon, and if you take actions to make it weak, then that's a control, I think. So if you drive a vehicle, we cannot go beyond what we can manipulate, of course. And what we can manipulate in case of typhoon, it's very limited. That's why some people may think that it's not really controlling because the manipulation power is too weak. But still, we aim at something and we set the goal or the target, and we are controlling a typhoon. My understanding.
Yeah, thank you so much for the project director. So, starting this project, so we are considering about that. So you said controlling and modifying the weather. That's so I just follow the controlling the word. But now it's a time we reconsider the term. So typhoon modification is better to match our research. So yeah, that's my opinion.
Okay. Let me respond quickly. So as I said at the beginning of this symposium, I recently published my own work on the theory, the duality principle between control and data assimilation. And we take the mathematical theory for control. So it's not just modifying again, we really control.
Yeah.
So this is the approach is a control. And if you just randomly modify, it's not the control. But what we aim at is controlling.
I see. Okay.
All right, let's thank speakers again. Thank you.